Okay, so today's tutorial is all about torsion, and I've picked out 4 different problems for us that are going to help you understand the concepts that were covered in the lecture materials for lectures 5 and 6. Anybody have any questions before we get started? Okay. So the first problem that we're going to look at together is problem 5.1. And let me just look at my screen and make sure that, nope, see, it's flipped the wrong way around. There we go. That must look better. All right. Okay, so we're going to look at problem 5.1 from the book. So in this problem, we have a Formula One race car, and I'll just draw the important components of the problem. Here we've got the engine, and then coming out of the engine, we have the drive shafts to the rear wheels, and there's 2 shafts, one to each of the wheels, and because they're 2 different shafts, they're called the half shafts. Okay, so I'll read the problem statement. Power from the engine of a Formula One race car will be transmitted to the rear wheels from the differential by 2 half shafts. So there are the wheels there. Here are the shafts there. Spinning them at 3,100 RPM. So we know that those shafts are going to be rotating at 3,100 RPM revolutions per minute. To minimize weight, the shafts will be made of carbon fiber with a shear strength of 13.1 KSI. So we know that the shear strength, and for carbon fiber is not a ductile material. Carbon fiber composite, it's a brittle material. So this would be the ultimate strength is 13.1 KSI. So that's our stress limit. The car can accommodate a maximum shaft diameter of 5.5 inches. So that's the maximum diameter of those shafts can be 5.5 inches. Rounding cross-sectional dimensions to the nearest 1/32 of an inch determine the percent weight reduction achievable by using a hollow shaft compared to a solid shaft of minimum allowable diameter. Okay, and just looking here, I did miss writing one thing on the board, and that was the sentence that said, at top speed, the engine transmits 780 horsepower to each shaft. So we've got 780 horsepower going to each shaft from the engine. So this is 708 horsepower per shaft. Okay. So again, determine the percentage weight reduction achievable by using a hollow shaft compared to a solid shaft. Okay, so what we want is percent weight reduction if using a hollow versus solid shaft is our question. Okay. Great. All right. So first of all, so we're taking this shaft and we want to design a solid shaft that is capable of supporting the internal torque that shaft is going to have to take, given the amount of torque being applied to it, which we can calculate by power equals T omega from these quantities. So we want to calculate the minimum size solid shaft that it would take to support this stress. and also the same thing for a hollow shaft, and then we'll compare the weights of those. And thinking about comparing the weights of those, we'd want to take the volume of the shaft multiplied by the density of carbon fiber. We don't have the density of carbon fiber here, but it doesn't make a difference because we're going to be doing a ratio of hollow shaft to solid shaft. So that density will cancel out. So the first thing, let's figure out how much torque is being applied to each one of these shafts. So if we take the top half shaft there, like this, the engine is applying some torque, T subscript E, for the torque from the engine. And if it's rotating at a constant velocity, some of the torques has to be equal to 0 for this shaft. So some of the torques has to be equal to 0. So where is the equal and opposite torque that is opposing the torque from the engine? Well, that's the torque that's coming from the wheel. So we've got in the other direction TW, the torque from the wheel. And we know some of the torques is equal to 0. TW has to be equal to TE. We can really easily calculate what TE is using our equation. Power equals torque multiplied by angular velocity in radians per second. Okay, power, we have power given in horsepower. When we're applying this equation, we're going to want our torque in pound-feet. So horsepower needs to be in pound-feet per second. We're given horsepower. The conversion factor is that 1 horsepower equals 550 pound-feet per second. So into this equation, we want 780 horsepower multiplied by 550 pound-feet per second per every 1 horsepower equals TE, the torque imparted to the shaft by the engine, multiplied by omega, our angular velocity. Okay, now we've got 3,100 in revolutions per minute. If you want to change that, that's easy. We've got 3,100 revolutions per minute. To change that into radians per second, which omega needs to be, then we want to multiply by, we want to get rid of revolutions, so that would go on the bottom, and the conversion is 1 revolution would be 2 pi radians. So there's our revolutions gone. And then we want to get rid of minutes and replace that by seconds. So we need minutes on the top, seconds on the bottom, and the conversion between minutes and seconds is 1 minute is 60 seconds, of course. There we go. So we need to multiply that 3,100 by 2 pi over 60 to get into radians per second. So we've got 3,100, 2 pi divided by 60. So that's going to give us the torque produced by the engine that's applied to the shaft. Let me see what I got when I did that. I got 1,321.5. 1,321.5, and that is in units of pound-feet. Everybody okay so far? All right, I'm just gonna make sure, double check that this is actually a recording today. Yep, so good, we're recording. All right. Okay, so now that we've got that, the thing to realize is if we take a section cut through this shaft here, there we go. We've got TE being applied there. Some of the torques has to equal 0 for the little portion of the shaft that we've got. So the internal torque, which I'll call TI, has to also be equal to the torque from the engine, or 1,321.5 pound-feet. So now that we've got this, now we can think about, let's start with the solid shaft because that's just, a touch easier. So we'll design, or we'll figure out what the smallest diameter solid shaft could be to support this torque, that internal torque, with only allowing the maximum shear stress to go up to 13.1 KSI. So what we're going to do is we're going to say we're going to equate, not sigma because we're dealing with shear stress, not normal stress. We're going to equate what the allowable shear stress is in our system, which is 13.1 KSI here. Normally allowable shear stress is the limiting shear stress, ultimate shear stress, or yield stress divided by the safety factor, but we're not told that there's a safety factor in this problem, so we're assuming that it's 1, and that makes sense if it's something like a Formula 1 car and you really want to maximize performance, right? You don't want any margin of extra safety that would add extra weight. So our allowable shear stress, we're going to set that equal to the maximum shear stress in the object, okay? So here, this is going to be our ultimate shear strength, and then the maximum shear stress. We've got our equation for shear stress due to torsion as tau is T rho over J, okay? Now, shear stress for something that's a circular cross-section that's experiencing an internal torque, we know that the magnitude of shear stress present increases moving radially outwards from the center. So if we draw the distribution of shear stress along this line here, the shear stress at the circumference will be greatest, and then the value of shear stress will decrease linearly to 0 moving towards the center. So the maximum shear stress is going to occur at any point all around the circumference. So when we take this equation and want to write maximum shear stress, we replace rho by the radius of the object, or in this case, we'll write diameter divided by 2, divided by j. Okay, so let's fill in some values here. 13.1 KSI was our ultimate strength, so we're going to put 13.1 times 10 to the 3 to change that to units of PSI. Remember, when you're dealing with equations involving stress in US units, you want pound, inches, PSI. So we're going to change that into PSI. Our torque is 1321.5, but that's in units of pound-feet, and we want pound-inches PSI, so we want to change this into pound-inches. So we're going to multiply by 12. Going to multiply by our diameter divided by 2. Our diameter is what we're looking for here, and divide it by J. J for something that's a solid circular cross-section. J, radius of gyration. It's like the moment of inertia, but for torsion, is pi over 2 radius to the 4th power. So we've got pi over 2 and then diameter divided by 2 radius to the 4th power there. So we can get rid of that one and get rid of that one and make that one a cube. So we've got D is equal to, what did I get when I did that? 1.83 inches. Okay, now in the problem statement, we were told that we have to round to the nearest 1/32 of an inch. So we need to round to the nearest 1/32 of an inch. The easiest way to determine, so we know we have 1 inch point something, and we need to figure out how many 30 seconds 0.83 is. The easiest thing to do is just take 0.83 and see how many times you can jam 1/32 into that. And if you do that division there, you will get 26.56. So 1/32 will go into 0.83 a bit more than 26 times. So there's the question now of whether we round our answer here. We have two choices. We could go 1 inch and 26/32, or we could go 1 inch 27/32 for the diameter. Okay. If we were to round down and choose 1 and 26/32, right? That would mean that we don't have the cross-sectional area that is needed to maintain the maximum stress at 13.1 KSI. And if we round down to 1 and 26/32, the actual maximum stress will exceed 13.1 times 10 to the 3 PSI, 13.1 KSI, and the shaft would break. So we need to round up in this case, okay? So this would be the required diameter that we need for the solid shaft, all right? Okay, just pause and see if anybody has a question about any of the calculations involving the stress over here. Okay, not hearing anything. Okay. Kind of lost after you go to the right. What do you mean? Over here? The part involving stress? Yep. So again, what we're doing is we're equating the allowable stress to the maximum stress in the shaft. This is the picture of our solid shaft, right? You know from the lecture material that a circular shaft or a circular rod or a circular object that's experiencing an internal torque will have maximum shear stress at the circumference, and you know that that maximum shear stress is given by the equation tau equals T rho over J, where rho is just any distance measured outwards from the center. So at the circumference, rho becomes R over J. So all we're doing is taking our internal torque. We found what the internal torque is that the shaft has to support. This is the radius here. And then J, radius of gyration, is just a property of the cross section. Okay, and the equation for that is pi over 2 radius to the 4th power for a solid circular shaft. Okay, so then we're just getting the diameter that the shaft needs to have in order for the maximum stress, which would be the stress again on the circumference, to hit a value of 13.1 KSI when the applied torque is 1321.5 pound-feet. Okay. All right. So we want to find percent weight reduction, right? So what is the weight associated with that diameter? Well, the weight of the solid shaft would be equal to what? It would be equal to whatever the volume of the solid shaft is multiplied by the specific weight of carbon fiber. So we'll use this as specific weight. Right, that's just density multiplied by acceleration due to gravity. Normally I just put density in there, but we've got rho being used up here as well, so I don't want to get you confused by putting two different rows on the board that mean different things. So we'll use specific weight. So the volume is equal to what? The volume is equal to whatever the length of the shaft is here, L, multiplied by the cross-sectional area of the solid shaft, multiplied by the specific weight of the material. So for the weight of the solid shaft, we have what? The variable L here multiplied by pi over 4d squared, where d is 1 27/32 squared, multiplied by our specific weight gamma there. Okay. So now what we need to do in order to determine the percent weight reduction achievable by using a hollow shaft, we need to do the same thing, but designing the shaft in the case of it being hollow. So let's do that. And then we can get the weight for the hollow shaft and then compare that to the weight of the solid shaft. Okay, so for the hollow shaft, right? So now we're going to be designing a shaft that looks like this. Again, it's going to have to carry the same internal torque that we had, the internal torque being 1,321.5 pound-feet. We know that, again, shear stress increases reaching, going outwards from the center. The material along the circumference, therefore, carries more of the torque that's being applied than the material in the center. The material in the center is at under zero shear stress, so it actually doesn't contribute to resisting this torque. So if you want to design a hollow shaft most efficiently, that is with minimum amount of material to carry an applied torque, you want to maximize your external diameter and then figure out what your internal diameter needs to be to meet your stress requirement. So we make our outer diameter the full 5.5 inches that it's allowed to be. Okay, so this is our outer diameter. We're going to set that equal to 5.5 inches. And then we're going to figure out what our internal diameter can be. How large can that internal diameter be before the stress at the outside here, which would be our maximum shear stress, equals 13.1 KSI. Again, we know that for any radial line connecting the center to the circumference, the shear stress will be greatest at the outside and will decrease linearly moving towards the center. Now, in this case, only the wall thickness here carries shear stress because there's no material on the inside, so that can't have a stress. So our stress profile in this case looks like this, where our maximum shear stress occurs right at the outside. Right. All right, so let's go ahead and do that calculation. So I'll erase some of this and make some room for us to do that. Okay. All right, so we're going to do the same thing. We're going to set the allowable stress equal to the maximum shear stress in the solid shaft. Again, we've got tau subscript u, the ultimate shear strength, being equal to, in this case, T rho, and the maximum value of rho here is the outer radius, or the outer diameter, divided by 2. So we've got DO divided by 2 there. And then down for J, we're going to put pi over 2, and then we have the outer radius to the 4th power minus pi over 2, the inner radius to the 4th power. Because when we're finding J for a hollow shaft, all that we're doing is we're taking the J value for a solid shaft with the outer diameter, which is pi over 2 radius to the 4th power, and then we're subtracting off the radius of gyration for the internal portion there. Okay, let's fill in some numbers here. So we've got 13.1 times 10 to the 3, 13.1 KSI. In units of PSI equals our torque, which was 1,321.5 pound-feet. We're multiplying that by 12 to change it into pound-inches. Then we're multiplying by DO divided by 2. Our maximum motor diameter can be 5.5 inches, so we've got 5.5 divided by 2 there. Divided, we factor out our pi over 2, so we've got pi over 2. And then we have our outer diameter again divided by 2, so 5.5 divided by 2, square that, nope, raise that to the 4th power, sorry. Subtract off your inner diameter, di divided by 2 to the 4th power, right? And that's what we're looking for, the inner diameter this time. Okay, so what did I get when I went through and solved that? I got inner diameter can be a maximum of 5.448 inches. Okay, so that's how big the internal diameter can be before the material at the circumference of that hollow shaft exceeds our ultimate strength for the carbon fiber. So again, we have to round this to the closest, the nearest 1/32. So we take 0.448 divided by 1/32 to see how many times that will fit inside that. And that comes out to 14.34 there. Okay, so now, again, you have the choice, right? You can round this to 5 and 14/32, or you can round to 5 and 15/32. Okay. Now, for the solid shaft, when we were rounding, we had to round that up so that we'd have slightly more material than we needed, and we wouldn't exceed the ultimate strength. You have to be smart about this. When you're doing a hollow shaft, right, you do not want to round up the value of internal diameter because that would give you less material than you need, right? If you need to round the internal diameter, you need to round it down to give slightly more material than is required. So we need to go with the smaller of those two. We need to round that number down in this case. All right, any questions now before we do the actual weight reduction calculation? Do some erasing on the board. Okay, not seeing anything, so I'll keep going. So, similarly, the weight of the hollow shaft would be equal to the volume of the hollow shaft multiplied by the same density or specific weight of the carbon fiber. And again, this would be equal to length, same variable L, because we're not changing the length of the shaft, we're just changing the cross-sectional properties between the solid and the hollow shaft. Area of the hollow shaft, and our value gamma here. So when we look at percent weight reduction, right here, we want the difference in the weights, right, between hollow and solid. So the weight of the solid shaft minus the weight of the hollow shaft divided by the weight of the solid shaft is the original comparison that we want to make. So we're comparing the difference between these two to the original, and then we'll multiply that by 100. So here for the weight of the solid shaft, we've got LAS gamma. The weight of the hollow shaft, we've got L area of the hollow shaft, gamma for the specific weight, and then for the weight of the solid shaft, again, we have LAS gamma. So even though we don't have the density of carbon fiber or the specific weight, that cancels out anyway, and so does the length of the shaft. So what we're really looking at here is just the ratio of cross-sectional areas to one another, or the difference over the area, cross-sectional area of the solid. So we can put everything in here, and this can be changed then to 1 minus AH divided by AS to make it even easier here. So 1 subtract area of the hollow, area of the solid. So the cross-sectional area of the hollow shaft will be pi divided by 4, and then the outer diameter, which is 5.5 squared, minus the inner diameter, which we said was 5 and 14/32. So we've got 5 and 14/32 squared, and then divided by the area of the solid shaft, pi over 4 d squared. So we had 1 and 27/32 for that, and square that. Okay, cancel off those. And doing that calculation gave me, what did it give me? 79.2%. Right, and then that would be final answer. So you have a much lighter shaft if you use a hollow shaft than if you use a solid shaft. A hollow shaft of minimal amount of material to support this stress can be much lighter than a solid shaft. Why? Because again, when you've got something that is experiencing an internal torque, shear stress is greatest at the outside, decreases moving towards the center. So all of the material in the center and around that adds to weight, but does not meaningfully support the internal torque, right? There's very little stress on it. So by removing that material and having a hollow shaft, you end up with something that is much better at supporting torque for its weight. Okay, questions about that problem before we erase it and move to the second problem? Okay, not seeing any, so we'll keep going here. All right, okay, fresh sheet of glass, ready for problem 2. So let's see what we've got for our second problem here. Okay, this is problem 5.2 from the book. So what we have are 2 pieces of wood, and I'm going to draw that so the piece of wood is a little bit thicker. So I have more room here. Okay, and here's a second piece of wood down below it. And we are joining those together with a screw here. So it's going down into the wood like that. And here's the small head of the screw like this. Okay. Okay, so that screw is being driven down into the wood by the torque being applied from a drill. So this is T subscript D for the torque from the drill. And then again, if it's being driven in at constant speed, then the torques have to be equal. Some of the torques has to be 0. And the counteracting torque here is coming from the wood. Okay, so it's applying a torque in the opposite direction. But in the problem, that torque, it's distributed along the length of the screw that's actually in the wood, which makes sense, but it's decreasing in magnitude moving to the tip of the screw. Okay, so we have a decreasing distributed torque that's appearing like that. Okay, so there we go. And we're going to call that T subscript W for the torque that is coming from the wood. And the total depth into the wood is variable D here. And we've got a little graph on the side of the problem that shows how the value of TW, the distributed torque, changes with depth. So we've got a little plot here that gives us the value of TW versus D. And the value of TW up at the surface of the wood is indicated as 115D. So whatever this value is here depends on the total depth into the wood we are. And the magnitude decreases linearly, moving to the bottom of the screw. Okay, so here's D there. All right, so that's how TW changes. And this is given in units of Newton meters per meter. All right, there, and this is in meters. Okay, so I'll read some of the actual problem statement now that I've got the important parts of the drawing on the board. A 4 millimeter diameter screw. So we've got a screw that is diameter 4 millimeters with 4.7 threads per centimeter, has a shear yield strength of 180 megapascals. So we've got tau y is 180 megapascals. and modulus of rigidity of 75 gigapascals. So that's our value. G is 75 gigapascals. Modulus of rigidity, the shear equivalent to modulus of elasticity. When driven into oak boards, the screw will experience the linearly distributed torque shown. Great. Okay, so a couple of different parts to this problem. Part one, what is the maximum depth D that the screw can be driven into the boards before yielding? Okay, so max depth into wood before screw yields. Okay, let's do that part first. All right, so again, we've got something under experiencing a torque. So what we want to do is the amount of applied torque has to equal the resultant of the distributed torque for some of the torques to be equal to 0. So as the screw goes deeper into the wood, the depth increases, so the total resultant distributed torque increases, which means TD increases. So that's going to be the limiting factor. So at some point, D will become so large that the maximum shear stress exceeds the yield strength. So what we want to do is equate our allowable stress to the maximum stress in the object. Now, our allowable stress in this case is simply equal to the yield strength because we want to determine the depth before the material actually yields, right? There's no safety factor, the safety factor is 1. And for the maximum shear stress here, again, we're using the equation tau equals T rho over J. But if we want maximum shear stress, the internal torque that we use, this should be the maximum internal torque that the screw experiences. Variable rho, we want to maximize that, so that becomes the diameter divided by 2, or the radius. And J, we know what J is. J is radius of gyration, cross-sectional property. So this is pretty easy, right? We've got J because we've got the diameter here. That means that we have that too. We've got the yield strength there. So all we need is what the maximum internal torque is. Okay. So let's look at the screw. First of all, where is the maximum internal torque in the screw going to be? Well, if we cut down right below the head of the screw here, there we go, there's our free body diagram. We've got TD like this, and our internal torque is going to be equal to TD because we have some of the torques need to be equal to 0. So internal torque equals TD. If we make a section cut any lower than that, we're going to have a little bit of the distributed torque in the diagram, and it's going in the opposite direction as TD. So the internal torque will start dropping, right? And the internal torque will continue to drop, going down and down and down until we get to the tip where the internal torque is 0. So at this location here, between the surface of the wood and the torque being applied to the drill, we have the maximum internal torque at that location. So this does equal our maximum internal torque here. So now we just need to figure out what that value is. And we can get that from TD, and we get TD by looking at the free body diagram of the whole screw. So for the whole screw, we know that we need sum of the torques equal to 0, which means that TD has to equal the resultant of the distributed torque, which is the area on this diagram. That area equals the resultant of that distributed torque. So this is just 1/2 base times height. The base here is distance d, and the height we're told is 115d. Okay, so there we go. So we've got TD now. So we can go back to this equation and put everything in. So I'll just write it again. TY is the maximum internal torque, diameter divided by 2 divided by J. So putting in some values now, we've got our shear yield strength is 180 megapascals. The maximum internal torque is going to be 115 divided by 2 multiplied by d squared. So 115 divided by 2 multiplied by d squared. And that's in units of what? 115d is in units of Newton meters per meter, and we're multiplying by meters. So we've got Newton meters as a unit there. That's good. We've got pascals there. Remember, in SI, we want pascals, newtons, and meters. D divided by 2. This is a different D than this D here. That D is depth and that D is diameter up there. Our diameter is 4 millimeters. So we want that in meters divided by 2 there. And then J, pi over 2 radius to the 4th power, pi over 2 and radius to the 4th power. 4 millimeters. There we go, divided by 2 to the 4th power. So that gives us D, which is the maximum depth that that screw can be driven into before the screw starts to yield, right? Where would it yield? It would yield on the outside of the screw, anywhere in between the surface of the wood and where the torque from the drill is being applied. Those are the points that are under maximum stress. So what did I get when I did that? I got 198 millimeters. You get 0.198 meters from this equation because it's coming out in units of meters. So this is 198 millimeters. Okay, questions about that portion of the problem before we move on to the next portion of the problem? I'm gonna get myself a drink of water while you guys think of questions that you have or that you want to ask. Okay, not seeing any. All right, so let's check out what the second portion of the problem is. I'll just do some erasing to give us some space for the second portion first. Okay, what do we have for the second portion of this problem? Here we go. Okay, part 2. If a 250 millimeter long screw is used, so we're going to say if this whole length here is 250 millimeters, okay. What will the screw's angle of twist at this depth being the depth found previously, be? Okay. So So what we want to do is find the total angle of twist for the screw when the depth D is equal to 198, the 198 millimeters that we found previously in part 1. Okay, so how are we going to go about this? Let's modify this drawing over here to just declutter it a little bit, and we'll change it into, well, it is a free body diagram, but we'll remove the wood to declutter it a little bit. And that will help us. Okay. There we go. All right, so let's connect the screw back together like this. Okay, there we go. All right, and we'll get rid of that section cut too that's shown through there. Okay, good. So we want the total angle of twist for the screw. So it's always helpful to label some points of interest on your diagram so that you can properly annotate the variables that you're using in your equations. So I'm going to call the top of this screw and we'll say that this length here for the total length of the screw is just up to the start of the head. We'll assume that the length of the head of the screw is negligibly small here in relationship to the 250 millimeters. So we're going to call this point here point A, and we'll call the bottom of the screw point B. Our equation for angle of twist is angle of twist phi is TL over JG, right? Very similar to the equation for axial deformation, NL over AE, right? We've got N, T instead of N, we've got an L in both of them, properties of the cross section, and slope of the stress strain diagram. All right, or the elastic portion of the stress strain diagram. Just like we did for axial deformation, we can only apply this equation to sections of an object that have constant values of T, J, and G over length L. So for our object here, because the applied torque changes over the length, then we're going to have to break this up into segments. Specifically, we're going to need to take a new point, an intermediate point C here, and say that the total angle of twist of the screw, which is phi from point A to point B, is going to be the angle of twist of segment AC plus the angle of twist of segment CB. Okay, break it up into two different segments. Okay, and then we can expand these two terms out. So for phi AC, this is going to be the torque in AC multiplied by the length of AC divided by J and G. And I'm not going to put subscripts A and C on these two variables down here because the screw has a constant diameter and it's all made of one material. So J and G for segment AC are the same as those variables for segment CB. Plus, now for segment CB, we can't use this form of the equation because the internal torque is going to change continuously over the length of segment CB because we've got a distributed torque. So we need to use the integral form of this equation. So that's going to be the integral from 0 to L, where L is the entire length of the distributed torque, or the length of segment CB. And then we've got our internal torque, T CB. Okay, this is going to be an equation that describes how the internal torque in segment CB varies with length. The variable that we're taking the integral with respect to over, again, J and G. So This is all looking pretty easy now. The only thing that we need is our internal torques here. We need TAC and we need TCB. So let's go ahead and get those. So we'll get our internal torque TAC by taking a section cut again like that. So we can do our section cut like this here, and TD is in this direction. We already said we knew the value of TD, right? We said that was 1/2 multiplied by the value of D, right, for the base of this triangle, multiplied by its height, 115D. So we've got the value of that. And now we've got D from our previous problem there. And then our internal torque, we've got TAC is equal to TD. Okay, now for TCB. Okay, so if we take a section cut through this and draw the free body diagram of one side of the object or the other side of the object, we reveal what that internal torque is, and we could write an equation for it. So you always want to do the portion of the free body diagram that's easier. So in this case, that's the bottom portion. So taking our section cut, right, there's our section cut. Here's the remainder of the screw, like this. There we go. Smaller. We just have a small portion of that distributed torque acting on this lower section of the screw now. So we've got some of that distributed torque like that. There we go. And this, we'll call this section of the screw length L long, and we'll measure it from the bottom upwards there. So that's our variable L when we conduct the integral. So we integrate from 0 to L, where here's our variable L, and L is going to end up being a maximum of 198 millimeters when we fill it in for our limit for our integral there. Okay, so counteracting this distributed torque here, first of all, what's the value here of the distributed torque at the top section here? Well, we know that the value of any point on this line depends on what the depth is, and its value is simply given by 115 multiplied by depth. So here, if this was our new variable L, then this, or I should do that so it corresponds actually to the location that I've drawn in the free body diagram. That would be smart. So here we go, right there. So we want to know what that value there is, H. Well, this is our distance L. So the value of H here would be 115 multiplied by whatever L is. So this is 115 L now. Okay, so this point here is 115 L, the value of the distributed torque there. Just label that as T. So the internal torque has to resist the resultant of the distributed torque. So that's going to be occurring around in the other direction, like that. So this is the internal torque TCB here. Okay, and we've got sum of the torques has to be equal to 0. So we've got TCB is equal to the resultant of the distributed torque, which would be 1/2 base, which is L, multiplied by height, 115 L. Okay. So now we've got, looking at this equation here, we've got everything that we need to go ahead and solve that. So let's plug some things in. I'll just check to make sure that there are no questions in the chat before we plow ahead and do that. But we've already done now all of the hard work. All that we need to do is the math that's left, with a little bit of attention paid to the signs of the numbers for internal torque that we put into the equation. Okay, not seeing anything in the chat. Okay, so let's take this line and we'll continue it up here. So the total angle of twist is going to equal, first term here, TAC. We know TAC is equal to TD, which is 1/2 115 d squared. Now, when we put an internal torque into an angle of twist equation and we're using superposition, we need to pay attention to the sign of the internal torque so we know whether to appropriately add or subtract terms. So for axial deformation, we did that by saying that any internal normal force that's compressive, we're going to assign a negative sign. For angle of twist, we do that by saying we're going to look at the sign of T by applying the right-hand rule, okay? So you do that by taking your right hand, and this is going to look to you like it's my left hand, but that's because the video is mirrored horizontally, so this is in fact my right hand. But you take your right hand, and what you want to do is you want to take the thumb of your right hand and you want to point it in a direction that is sticking out of the section cut that you've made. So you want to point your thumb in the direction of that arrow, and then your fingers curl in the direction of a positive internal torque. Now, my fingers are curling in the opposite direction to what I've shown as the direction of TAC. So this value here, which TAC is equal to, needs to go in to this variable as a negative. So we need to put in negative 115 divided by 2. So there's the 115 divided by 2. And then the d squared, we said that d, right, for the depth in 1, so d is 198 millimeters now, or 0.198 meters. 0.198 and squared. Okay, and then we put in LAC, so that's just the length of segment AC. So the depth now is equal to 198 millimeters. So that means we're taking the difference between 250 and 198 to get the length of AC. So we've got 0.25 minus 0.198 there. And then we're dividing by JG. Okay, so divide by pi over 2 radius to the 4th power. So we've got 0.004 for the diameter of the screw divided by 2, raise that to the 4th power. And then G is the modulus of rigidity, 75 gigapascals. So we've got 75 times 10 to the 9 there. Okay. And of course, we could have factored that out and put it outside, but I'm doing it below each term just because I'm writing the equation here on 2 different lines, right? Continuing now on to the second line, adding on the second term here. Okay, so now we want to do the integral from 0 to L, where L is the total depth, so 0.198. And now we put in the expression for TCB. So the expression for TCB is 115 divided by 2L squared. So 115 divided by 2L squared. But again, you need to pay attention to the sign of this internal torque. So again, take your right hand, look at where your section cut is. So this is my section cut here, right? Take your thumb and point it sticking out of that section cut. So that's in the direction of that arrow there. And then your fingers curl in the direction of a positive internal torque. TCB is oriented in the opposite direction, so it's a negative internal torque. So this needs to have a negative sign in front of it like that. Then we've got DL. And then we've got J and G, which is the same quantity, pi over 2, 0.004 divided by 2, raise that to the 4th power, and then 75 gigapascals. There, that's times 10 to the 9. Okay. Angle of twists are always going to come out in units of radians here. So this number will come out in terms of units of radians. And what did I get when I did that? I got minus 0.1413 rad. Okay. Now, it's hard to picture what 0.1413 radians is, so it's quite common to re-represent this as a number in degrees by, of course, multiplying by 180 over pi, or whatever conversion factor between radians and degrees that you want to use is. So that would give us minus 8.1 degrees. Okay, so what does the negative in front of this number mean? That means that what is the actual direction of angle of twist? Well, a positive angle of twist is given by, again, the right-hand rule. Because we were using the right-hand rule to pick the signs for internal torques, the sign of the resulting angle of twist is also given by the right-hand rule. So what you do is you take the thumb of your right hand, direct it along the length of the screw. Your fingers curl in what would be the direction of a positive angle of twist. And the angle of twist is negative, so that means that the relative to the bottom, if that's fixed, that the top actually rotated in the opposite direction by 8.1 degrees. And of course, that direction makes sense because the top of the screw would twist in the direction that the torque from the drill is being applied in. Okay. If the problem had have been drawn with the torque going in the opposite direction, right, then our value here would have come out as a positive value. Okay, questions about that problem from anybody? Yes, this tutorial is being recorded. It will be recorded and then it will be posted at some point later today after the video file finishes its encoding. Last week I recorded the Wednesdays tutorial instead of the Fridays, but today I'm recording the Fridays tutorial. Okay, no questions about the material on the glass from anybody before I start erasing? Going once, going twice. Okay, let's start doing some erasing. How is the level of smudging on the board with this new color marker? Let's see. Yeah, it's okay. It's not quite as good as the other markers, but it's okay. Okay. I think we're ready for the third problem now. So let's see what we've got here. This is problem 6.3 from the book. We have got a rod here that is fixed to walls or supports at either end. And it has a uniform distributed torque over a portion of its length. Okay, so the lengths here, the total length of the distributed torque, it's over a distance or a length of 250 millimeters, and then we've got another 50 millimeters here before we get to the wall. And on this side, we've got a length of 500 millimeters there. And the distributed torque has a value of just a value of an unknown value T, Newton meters per meter. Okay. All right, let's see what the problem statement says. The problem statement says the 30 millimeter diameter 6061 T6 aluminum shaft. So it's a diameter of 30 millimeters. It's 6061 T6 aluminum with a yield strength, shear yield strength of 131 megapascals. Will be loaded as shown. For a safety factor of 2.5, so we've got safety factor of 2.5. For a safety factor of 2.5, determine the maximum allowable value of the uniform distributed torque T. Okay. So we want to know for our safety factor equals 2.5. Max value of distributed torque. Max value of the distributed torque T. Okay, so what can be the maximum value of the distributed torque T if we've got a safety factor of 2.5? Okay, this is the same sort of deal as the other problems that we've been looking at, right? What we want to do is we want to equate the allowable shear stress to the maximum shear stress that this object is going to sustain. So the allowable shear stress here comes from the shear yield strength divided by the safety factor. And then we're using our equation tau equals T rho over J here to calculate what the maximum shear stress is going to be in this object. So what's the maximum shear stress going to be? Well, it's going to be longitudinally along the object wherever torque, internal torque is maximum. So here we've got maximum internal torque. And maybe actually I'm going to change this to TI max just so that it's clear that this is internal maximum torque and not Tmax in as far as this being T as well. So this is the internal maximum torque multiplied by wherever the maximum internal torque occurs along the length in the cross section at that location. The maximum shear stress will occur when variable rho is maximized. And again, that's at the circumference. So this is going to be the diameter divided by 2. And then we've got the radius of gyration down below. Okay. So now looking at what we have, we've got D, right? D is 30 millimeters. That means we've got J. We've got Ty, that's 131 megapascals. We've got our safety factor. So the only thing that we need now is the maximum internal torque. Okay. So let's do some labeling on this diagram first of all. So let's call this point A, and then the start of the distributed torque point B, the end of the distributed torque point C, and the wall on the other side point D. Okay. So in terms of looking at internal torques, right, we could look at the internal torque between A and B. And if we do that, what do we have? Well, first of all, let's change this to a free body diagram. So let's erase our supports here. And we've got a distributed torque in that direction. So the torque at the supports is going to be in the opposite direction. So here's the torque at support A, and here's the torque at support D there. So going to our free body diagram here was the direction of TA that I drew up here. Very important that you maintain the direction of these arrows on your free body diagrams between sections of an object that you draw and the full free body diagram of the object. And then our internal torque, TAB, is going to be in the opposite direction of that. Okay, so we can't find out what TAB is until we know what TA is. If we take a section cut there, okay, here we go. Then we've got the orientation of TD like this, and the direction of the internal torque, TCD, would have to be in that orientation. So similarly, we can't find what the internal torque TCD is until we know what the support reaction TD is. Okay, so to find internal torques, need our support reaction torques first. Right, so we need our support reaction torques in order to find our internal torques. So let's write an equation of statics. Sum of the torques is equal to 0 for the whole free body diagram. Okay, so for the whole object, we know that sum of the torques has to be equal to 0. So doing that, we've got TA and TD are both in the same direction. So we've got TA plus TD is equal to the total torque in the other direction, which is the resultant of our distributed torque. The resultant of our distributed torque is given by the value of T multiplied by the length that it's acting over. So we've got T multiplied by 250 millimeters. We want to put that in units of meters, 0.25. Okay. So now we've got an equation from statics that says the summation of our support reaction torques has to be equal to the total applied torque, right? The problem is that we've got no way of knowing how much of this applied torque goes into support A and how much goes into support D. So this is one of those problems that's statically indeterminate, right? We can't figure out TA and TD in terms of T without another equation. So let's just label this here as equation 1. So we need another equation with these same variables in it in order to solve. And where does that come from? Well, when you've got a statically indeterminate problem, you look at deformations of the object to build up another equation. So in this case, where it's torques, we look at what the angle of twist of this object is going to be and see whether we can create an equation based on that. So what we know about this rod is that because it's fixed at both ends, that end A cannot twist relative to end D, right? They're both fixed, so one cannot twist relative to the other. They're both fixed. So the total angle of twist from A to D has to be equal to 0, right? So if we think about the angle of twist from A to D, right, we can't compute that as one overall angle of twist. We need to break that up into different segments using superposition. So we can say that angle of twist A to D equals 0, and the angle of twist A to D equals what? It's the angle of twist from A to B plus the angle of twist from B to C plus the angle of twist from C to D. So there we go. So let's take this portion of the equation here now and expand it out. So we've got 0 equals. So the angle of twist of segment AB will be the internal torque in AB multiplied by the length of AB divided by JG, modulus of rigidity, radius of gyration. And I'm not putting subscripts A and B down here because those two quantities are the same over the entire length of the rod. Then we can do term 2. Now for BC, this section of the rod has a distributed torque on it, and whenever you have something that experiences a distributed load or a distributed torque, the internal forces are going to change continuously over the length. So we need to use the integral form of the angle of twist equation. So we've got the integral from 0 to L of TBC dL over JG plus, now our final term, the internal torque in CD, length of CD over JG. Now we've got JG's in the denominator of each term and a 0 on the other side, so we can multiply both sides of the equation by JG and get rid of those. So now, again, we had one equation that had TA and TD in it, and T on the other side, T being our distributed torque. If we could get a second equation that had the support reactions in it, then we might have enough to be able to solve for both of those in terms of our applied torque T. And we've got internal torques here, and looking at our free body diagrams here, yeah, we can substitute in our internal torques for our support reaction torques, okay? From sum of the torques is equal to 0 for this little free body diagram here. We know that TAB has to be equal to TA. And for this free body diagram down here, we similarly know that TCD needs to be equal to whatever the value of TD is, okay? So we still need the internal torque in TBC. So let's go ahead and get that. So let's erase on the board there because we've got our internal torque TAB, we've got our internal torque TCD. Now we just need our internal torque TBC, and we should be okay to solve. So we'll get that internal torque that we still need. Okay, so we'll do a section cut between B and C, and then I'm going to draw the right-hand portion of that rod there. So we've got something that's like this, where our internal or our support reaction torque TD is around in that direction. And then we've just got a little bit of the distributed torque acting on this object. Right, so this has a value of T. And then we've got our internal torque. So I'm going to say that the internal torque here, TBC, is in the same direction as T. It doesn't matter which direction you choose for your internal torque. You just have to pay attention to the sign of it for your right-hand rule and create your equations of statics appropriately for this section. So for this section right here, we know that sum of the torques has to be equal to 0. So we've got TBC plus the resultant of T is equal to TD, right? And I'm going to define the location of our section cut as some distance L away from the start of the distributed torque, which is at point C there. So L is measured from point C to the location of the section cut that I'm doing right here. So we've got TBC plus the distributed torque, or the resultant from that, which is given by T multiplied by L, is equal to the torque in the other direction, which is T subscript D. Okay, so that gives us what? That gives us TBC is equal to TD minus T multiplied by length L. So now we've got an expression for the distributed internal torque in segment BC. Okay, let's just pause and see if anybody has a question before we go further. Okay, let's keep going then. All right. So let's go back to this equation and fill some things in. So we have 0 equals TAB. TAB is TA. Okay. But again, when you're doing superposition, you need to pay attention to the directions of these internal torques. So you go over to your free body diagram and use your right-hand rule to determine whether TAB is a positive or negative internal torque. So thumb points out of the section cut in the direction of the arrow. Fingers curl in the direction of a positive internal torque. They're curling in the opposite direction that I've drawn TAB in. So this needs to be a negative when it goes in that equation. Okay. So we've got negative TA there. Then we've got the length of segment AB. That's 500 millimeters, 0.5. Okay. Now we're adding on the integral. So we're integrating over the entire length of the distributed torque, which is 250 millimeters, 0.25 meters. And here goes the expression for TBC in for that. Okay. So that is TD minus T multiplied by L, and then we've got DL there. Now again, we have to pay attention to what the sign of TBC should be. So go over to your free body diagram. Here's my section cut for this free body diagram. Thumb points out of the section cut, so that's like that. Fingers curl in the direction of a positive internal torque. TBC is positive in the direction that I've drawn it, so this can just stay as a positive there. Okay, it doesn't need to change. All right, final term, TCD. TCD is equal to TD, so we can put TD in there. And then we've got LCD, which is the 50 millimeter length, so 0.05. And again, check the sign of TD. So where's our section cut? Our section cut is that section there. Thumb points out of the section cut in the direction of the arrow. There, fingers curl in the direction of a positive internal torque. They are curling in the direction of TCD, so that can stay as a positive there as well. So now we've got an equation that has TA, TD, TD, and T in it. Good. We've got two equations now with three variables. So we can solve those two equations together to be able to write both TA and TD in terms of only variable T. So what we do is write solving 1 and 2 together gives us TA equals TD equal. And this isn't a math class, so I don't need to actually see how you solve those simultaneous system of equations. So on your assignment or something, you can just do exactly what I'm doing here. Label the two equations, then write solving 1 and 2 and put the answers. All right, so what did I get when I did that? I got TA was 0.0547 multiplied by T, and TD was 0.1953 multiplied by T. Perfect. Okay, so what we wanted to do was find, remember, we wanted to find the maximum internal torque here. We know that TA is the internal torque TAB, or TAB is equal to TA. And we know that the internal torque TCD is equal to TD. So the internal torque TCD is clearly higher than the internal torque TAB. And between those two, so here's where TAB is, through that line there. Here is where TCD is there. Moving our section cut from TCD over to TAB, we're going through this distributed torque. So we just have to, as we move that section cut, we change between those two values in terms of the internal torque. So anything in between B and C has to be an internal torque that is an intermediate value between the value of TAB and TCD. So therefore, we know that TCD is our maximum internal torque. So this tells us, therefore, by inspection, right, the internal torque TCD equals TD is our internal maximum torque. Okay, so now let's go ahead and solve the problem. So I'll erase right here and just continue right below that line. Okay, so not seeing anything in the chat, so we'll keep going. 131 megapascals was TY. So we've got 131 times 10 to the 6. Our safety factor was 2.5. So we're putting 2.5 there. Maximum internal torque is TCD, which is equal to TD, and TD is 0.1953 multiplied by our value of the distributed torque T. Diameter divided by 2, diameter was what, 30 millimeters. So 0.03 divided by 2 divided by J is pi over 4, pi over 2, sorry. Radius to the 4th power, 0.03 divided by 2 to the 4th power. There we go. Okay, so from this comes what the maximum allowable value of our distributed torque T is. For me, that came out to 1,422.3, and this is Newton meters per meter. Okay. Anybody have a question about that problem before we move on to the 4th and final problem for this tutorial? Okay, quiet group today. Okay, that'll get us started. Let's see what we've got for the final one. Okay, this is problem 6.5 from the book. So in this problem, we have 2 shafts that are connected by gears. So we've got one shaft here. There we go. Okay, gear on the end of it. And that shaft is rigidly fixed at that end like that. And then we've got this gear is meshing with a larger gear. Okay, like this. And that gear is connected to a shaft like this. And that shaft has also a smaller gear on it, like this. And then it is also fixed, like that. Okay, let's put some dimensions on here. So the diameter of that gear is 250 millimeters. The diameter of that gear is 400 millimeters. And the diameter of this gear there is 80 millimeters. Okay. And the length of this shaft here is 1 meter. The length of that portion of that shaft is 200 millimeters. And then from there to the other gear is 90 millimeters. Okay. All right, the problem statement says the shafts have a diameter of 50 millimeters and are made from 2014 T6 aluminum with shear yield strength 172 megapascals. So the shafts. So that applies to both of these two shafts. So the diameter for the shafts is 50 millimeters. They're made of 2014 T6 aluminum, and that we're told has a shear yield strength of 172 megapascals. Determine the maximum torque that can be applied to the 80 millimeter gear. Okay, so we're applying a torque here to that gear for a safety factor of 2. Okay. So max torque on 80 millimeter gear for a safety factor of 2. And that's the question that we want to answer. So the approach to this problem is actually exactly the same as the approach to the previous problem, right? Because we've got an allowable stress here, the allowable stress being the yield stress divided by the safety factor. And we are going to want to equate that to what the maximum stress is in the shafts. And what the maximum stress is in the shafts will be a function of that torque that's applied to gear D. Okay, so that's the approach for solving the problem, is we want to say that the allowable stress will be equal to the maximum shear stress, and then we'll say that the allowable stress is the shear yield strength divided by the safety factor, and our maximum shear stress is going to be given by whatever the maximum internal torque is. And again, I'll just change this to TI max, just to make it abundantly clear that we're talking about maximum internal torque here, multiplied by the radius of the cross section, because it's at the circumference that the maximum shear stress will occur, divided by J. So again, all that we actually need to do to answer this problem is figure out what the maximum internal torque here is in these two shafts in terms of the torque being applied to this smaller gear here. So to help us keep everything straight in terms of the math, we should label the different points of interest on this diagram. So I'll just start from up here. So this point A, we'll say on the wall there. Here's point B, this gear, point C, point D, and point E over on the other wall. So A, B, C, D, E. Okay. So this torque being applied to gear D then is T subscript D for the torque being applied to gear D. So we want to find the internal torques in these two shafts, shaft AB and shaft CE, in terms of the applied torque TD. And after we do that and figure out which internal torque is the largest, we've got 3 options for internal torque. We'll have one internal torque in this section, one internal torque here, and a different internal torque here. And once we know what the largest of those 3 internal torques is in terms of TD, then we can solve our equation. Okay. So for finding the internal torques, again, this is a situation where we recognize that if we do a section cut at these different locations, we're not going to be able to find internal torque directly. We need to find what internal torque is in terms of support reaction. So we need the support reaction torques first. A good way to get the support reactions is by drawing free body diagrams of the two shafts separated from one another. So let's draw those. So I'll draw the top shaft first. So I think it's helpful here to kind of draw it in 3 dimensions. So there we go. That's the top shaft. So this is point A over there, and this is point B there. And then we've got the lower shaft right below that. Okay, there we go. So shaft, and it's going out like this, and then it goes into the smaller gear here, comes out the other side, something like that. Okay. All right, so if I put the direction, and this is, again, this is point E, here's point D, and over here is then point C. Okay, so if I put the applied torque TD on this diagram in the direction that I've drawn it, it is like this, T subscript D. And then counteracting that applied torque will be the torque at support E. So this is going to be in the other direction. So it's going to be opposing TD. So here's TE, and I'll just move my label and put it down there. And then we've also got the top gear that's meshed with, or gear B that's meshed with gear C, will apply a torque that opposes TD as well. So this will come from the force from gear B on gear C at the point where they contact, right? So this force is going to be oriented sort of tangent to the circumference here and over in this direction. So we'll just call this F. And force F creates a torque because it is at torque arm R, we'll call this RC, the radius of gear C, from the center of the shaft. Okay. So in terms of an equation of statics for the bottom shaft here, right, we've got, let's say for shaft, what is this? For shaft CE, we've got sum of the torques has to be equal to 0. Okay, so that gives us TE plus the torque from force F, TE plus force F multiplied by RC, right, that's torque now, is equal to the torque being applied to gear D, which is TD. Okay, there we go. So we've got one equation. Okay, for the top shaft, if force F, which exists at the contact point between these two gears, is in this direction, then it has to be the equal and opposite on the other gear. Okay, so there's F there, and it's at a distance of RB, the radius of gear B, from the center of shaft AB, so that's going to create a torque. Opposing that torque has to be the torque from the wall. Here's T subscript A. So for the bottom shaft, or for, should have said for the top shaft, but which is shaft AB. For shaft AB, the sum of the torques also has to be 0 for that shaft. So we've got TA equals F multiplied by RB. Okay, there's a second equation. Okay, so we're on our way to getting multiple different equations here that have the support reaction torques, so we can solve for those in terms of what we want, which is the applied torque TD. Okay, so what else can we do? Let's count our unknowns. So we've got 1 unknown, 2 unknowns, 3 unknowns. We know what RC and RB are, so those aren't unknowns. We've got too many unknowns for the equations that we have to solve them, so we need another equation. Okay, again, so that means that this problem is one of the statically indeterminate problems again. So we have to consider deformations to build up that extra equation. So what can we say? Well, this end is fixed here at E. This end is fixed at A. But in this case, we can't do what we did in the last problem and say that the angle of twist from E to A equals 0. That's not true because we have 2 different shafts that are connected at a point that can actually move. So this is not true in this case. So we need to think of another way to write another equation. So the way that you can do this is by considering the movement of these 2 gears. Because they're connected together and both gears have teeth, and that means that they can't slip relative to one another as they twist. So the twist in one has to be related to the twist in the other. And we can look at how that relation works by just looking at the ends of the gears here. So if that's the point of contact, and that's the center there, and this is the radius of gear B, and this is the radius of gear C. If gear B twists in the counterclockwise direction, let's say, and this point moves over to there, okay? That linear distance traveled has to be the same linear distance that the other gear travels, okay? So this distance here, we'll call that some linear distance SB, and this linear distance here, or circumferential distance SC, they have to be the same. So if no slip between gears, then SB, the circumferential distance SB, has to be equal to the circumferential distance SC. Okay? And then we can relate those to angles of twist, actually. Because the gears are connected to shafts. So we know that if we're dealing in radians, that a circumferential distance can always be represented as the product of the radius and the angle swept out by that circumferential distance, right? So this angle here we'll call phi B, right, for the angle that gear B twists through, and phi B has to be equal to, or SB has to be equal to phi B multiplied by RB. SB equals phi B multiplied by RB, okay, if we're dealing in radians, okay? And similarly, the angle here, we can call this angle phi C for the angle that gear C rotates through. The circumferential distance SC has to be equal to phi C multiplied by RC. Okay? Because these two things are equal to one another, we can say that phi B multiplied by RB has to be equal to phi C multiplied by the radius of gear C, RC. Okay? I'm going to pause there and just make sure that nobody has a question about that portion there. Everybody's following with that. Okay. So what we can do now is recognize that the angle of twist for gear B is going to be the same as the angle of twist for shaft AB, right? If point A is fixed and gear B twists by 5 degrees, then it must be that shaft AB also twists by 5 degrees. So we can replace phi B here by phi AB. RB. And similarly, we can replace phi C, the angle of twist of gear C, by the angle of twist of shaft CE. CE multiplied by RC. Okay. Great. Now we're on our way to getting a third equation that's useful. So I'm going to do some erasing over here to give us the space that we need to finish off this problem. Okay, so let's continue this equation. We'll use the angle of twist equation that we have. Phi is equal to TL over JG to expand both of these terms out. So phi AB is going to be the torque in segment AB multiplied by the length of segment AB divided by JG. Again, leaving subscripts off those because both shafts are the same material and same cross section. Radius of B on gear B equals the same quantity for shaft CE. Now for shaft CE, actually, looking down here, we need to break that up into two different segments because we've got an applied torque that occurs along its length. So we know that the internal torque in between D and E will be different than the internal torque between D and C. So we need to change this here to the angle of twist from D to E plus the angle of twist from C to D. And then that's all multiplied by RC. There we go. Okay, so I'll put the RC first to get that out of the way. And actually, you know what I'll do? I'll divide through by RC so it's under the RB, and then we'll have it completely out of the way from there. So we've got RC there. Okay, so now we've got the angle of twist of DE is going to be the torque in DE, the length of DE over J and G, plus the length of CD, or the torque in CD, sorry, length of CD over J and G. Okay, now we can cancel off the J and G's from all these terms because they're all common. And we can think about filling in the internal torques in terms of our support reactions, right? That's easy to do. All we need to do is take some section cuts to enable us to do that. So let's get the internal torques in all the different locations that we're going to need. So taking a section cut in between A and B. Okay, we've got a cross section right there. And here's our torque TA. Again, important to maintain the directionality of these torque vectors when you go from the full free body diagram for the shaft to just a portion of it. This means for some of the torques to be equal to 0 that our internal torque needs to be in the other direction. So this is internal torque TAB now, and it has to be equal in value to TA for some of the torques to be equal to 0, right? That's just some of the torques is equal to 0 there. All right, let's do another section cut in between E and D to figure out what TED is. So similarly, we've got TE around in this direction here and TED must be in the opposite direction, and it must be equal in magnitude to TE for the sum of the torques to be equal to 0 for this small free body diagram here. And then one final one, a section cut through there. And again, I'm going to draw the left-hand portion of this. So we've got a free body diagram now that looks like this, where this is TE. We've also got TD applied. And I'm not drawing the gear there, but the gear is there. So this point D here. And then I've got the internal torque, TCD. Now, it's unclear what the proper direction of that internal torque is, but it doesn't matter that you get the proper direction correctly. Just guess one of the two. So I'm going to put mine in this direction, which is the same direction as TE. So this is TCD here. And if we do sum of the torques is equal to 0 for this free body diagram, then we have TCD plus TE has to be equal to TD. So TCD is equal to TD minus TE. There we go. So now we've got an expression for the internal torque TCD. Okay, so we can continue with this equation up here down on this next line below those free body diagrams now. So let's substitute in for the internal torques in terms of the support reactions, and then we could get another equation that would have the support reaction torques in that we could solve with these two equations involving the support reactions that we've already got. So TAB is TA. There we go. But remember, when you put it into the equation for angle of twist and you're using superposition, you need to make sure that you get the signs correct. So here you want to use your right-hand rule with your thumb pointing outwards from the section cut. That's in this direction. Fingers curl in the direction of a positive internal torque. They're curling in the opposite direction of TA, so this needs to be a negative there. Then we've got the length of segment AB, which was 1 meter. That's gone from the glass now, but up earlier you would have seen that this whole length here was 1 meter. And we have RB divided by RC. So the radius of gear B was 250 millimeters. So we've got 0.25, that was the diameter actually, so we're dividing that by 2. And then the diameter of gear C was 400 millimeters, so we're dividing that by 2 to get radius. And of course your 2's cancel out here. So you're just left with 0.25 over 0.4. So then on the other side of the equation, TDE now. TDE is right here, and it's equal to TE in magnitude. Again, direction makes a difference, so use your right-hand rule, thumb pointing out from the section cut in that direction. Your fingers curl in the direction of TE, so that stays as a positive value, and then we multiply by the length of segment DE, which is just that length there. So here's LDE. And that from the earlier diagram was 200 millimeters, so 0.2. Finally, plus TCD is what? TCD is TD minus TE here, this term right here. Okay. And I'm going to erase this now so we're not so cluttered. Go. Perfect. TDE, and we've got LCD there, which was 90 millimeters, so 0.09. And we have to pay attention to the sign of this internal torque here, which is TCD. So again, right-hand rule, thumb points out of the section cut in the direction of that arrow, and fingers curl in the direction of positive internal torque. They're curling in the opposite direction to TCD, so this expression here needs to be a negative. Okay. All right, so now we've got another equation with our support reaction torques in it. So this is equation 3. Now we've got enough equations to actually solve for our support reaction torques, TE and TD. So we can do the same thing and just simply say solving 1, 2, and 3. In this case, we get values for TE and TA. And we want those both in terms of our applied torque, TD. So let's see what I got when I did the math on that. Okay, I got TE equals 0.203 TD, and TA is 0.498 TD. Okay. All right, so what we wanted was actually our internal torques, because going back to the problem, right, what we're looking for is our maximum internal torque. This is all to find the maximum internal torque. So what are our internal torques? So we've got TAB equals TA. So this is TAB here. And TE, right, that was the same as TED. Okay, TE was TED. So we know what this internal torque is. We know what this internal torque is here. We don't know yet what TCD is, but now we can find that out very easily because TCD is just TD minus TE. So we've got TD minus, what's TE? TE is 0.203 TD. So that gives us 1 minus 0.203. That's 0.797 TD. Okay. So here's one internal torque, 0.797 TD, 0.498 TD, and 0.203 TD. So what's the maximum internal torque? The maximum internal torque is the torque in segment CD right here. This is TI max right there. Okay, so that's exactly what we need to solve the problem now. So let's go ahead and do that. So bring this equation up to this line here. We've got the yield strength for the shafts, which we were told was what? 172 megapascals. 172 times 10 to the 6 divided by our safety factor, which was 2. Safety factor of 2 equals our maximum internal torque, which is 0.797 TD. 0.797 TD. Our diameter divided by 2. The shafts were 50 millimeters in diameter. So 0.05 divided by 2 divided by J, pi over 2 radius to the 4th power. Okay. And then out of that comes TD. Okay. So let's see what we get for an answer for that. 2,648.3 Newton meters. 2,648.3 Newton meters. That's the largest value that you can apply to that gear at D, the 80 millimeter gear, before your stress, your maximum stress in those two shafts reaches 172 divided by 2 megapascals. So this is 2.6 kilonewton meters, not kilonewton per meter, kilonewton meters. There we go. Okay. All right. So that brings us to the end of that problem there. So anybody have questions about that problem? Longer problem, not difficult after you know that the thing to look at is relating the circumferential distance traveled by each of those two connected gears. But a good problem in terms of figuring out for yourself whether you understand the right-hand rule and how that's used for superposition and being able to do that. You might be wondering, right? It seems like kind of an odd problem where we'd have a gear here connected to another gear, right? And here's another gear. Here's our other shaft, and have both of those shafts fixed and a torque being applied, right? Why are we looking at a problem that's so weird where we have something being torqued and both shafts are fixed? This is what would happen if you had a motor driving this gear, and then let's say that this shaft was normally going to drive some load like a fan or a pump or some other industrial process, and that load, the fan or the pump, became jammed, and so the whole assembly stalled, and the motor was still putting input torque in, but the shafts weren't rotating, right? This is what this sort of problem represents, just in case you were wondering physically when would something like this be encountered. Okay, any questions about this from anybody, or questions about anything from the course in general before I sign off?